All right, welcome to Discrete Math class. We are going to pretend to be good students. Good. We are recording class today because of a Bugs field trip. So Bugs field trip people and other weirdos who might feel the desire to be watching this. This is February 25th? 4th?
Yeah.
And we are in Discrete Math. It's Wednesday. Here's what we're going to do today. There was a homework which looked possibly from Edline like, oh yeah, it's just 3 problems, everything will be fine. No, it was really, really hard because it's math, and math is really, really hard until you learn it, and then it was like 6. Anyway, so we're going to go over that homework. Hopefully this will take 20 to 25 minutes max. Then I want to do a little theorem that we skipped, which is actually important to go over in order to be able to do the homework, so actually we'll do that first. And then we will learn some things that you kind of know and kind of don't know. Are you ready? Good. I'm a little bit sick, so I'm feeling a little bit stupid. Just a cold, I'll be fine. Yes, you can. Alright, so everyone please take out the homework. And let's go. Oh, no. Sorry. Before we go over it, there's an important theorem. It is called the prime divisibility property. It was kind of required to be able to do this homework, in my opinion. It was in the textbook, so it's not like I was hiding it from you. It was sitting right there. We just didn't specifically address it in class yet. Alright, what is the prime divisibility property? It is another one of these extremely low-level facts, number theory facts. And, well, whatever. It goes like this. I think I might be able to just do this off the top of my head. I think I understand this now. Prime divisibility property. It says, it says that if a prime divides the product of a whole bunch of those numbers, it must divide one of those numbers. Yeah. So, here it is. It's right there on the bottom, by the way, of page 114. It says, let P be a prime. Did we do this? I feel like we did it. Nope. Let P be a prime if P divides, and I'm just going to call this A1, A2, A, because it doesn't really matter, N. Then P divides at least one of the basic numbers. Okay, this states something which seems really obviously true. If a prime number divides the product of one of them, then it must divide one of them. By the way, is this true in general for not primes? No. Can you give me an example? Actually, that was one of the homework problems, I believe. Was it not?
Yes.
Number maybe like 30 or something? No. 38 says, hey guys, prove or find a counterexample. Well, this one's false, so hopefully you found a counterexample as opposed to proving it. And it is like the prime divisibility property, but without the condition that the divisor be prime, and therefore the thing is false. 38 says A is a positive integer, and B and C are integers. Consider the following proposition. If A divides BC, then A divides B, or A divides C. I claim this is false. Can we get a counterexample?
16.
No.
A is 8, B is 4, C is 2.
A is 8, B is 4, C is 2. That works. 8 divides 8, but 8 does not divide 4 or 2. Okay, I'll take it. All right, but so this is false.
I don't know.
Number 38. Okay, well, for primes, however, that trick of his kind of isn't going to work. Do you guys sort of feel that this has to be true?
Yeah.
Right, yeah. If the prime goes into the product of all these numbers, it must go into one of them, because it's not like the prime can be broken up into smaller bits that you can reconstitute from the various other factors. Okay, let's prove it. This proof is surprisingly technical and subtle, in my opinion. So, in fact, it is proven in two cases. Case one is the case in which the product of the numbers has just two factors, and case two is something else. Okay, so case one. Case one is n equals 2. In other words, p divides just two numbers. So what I now need to show is if p divides a1 times a2, then p divides a1 or p divides a2. In other words, like the thing we just did, but this time with primes, it'll be true. Okay. Well, let's do it. Let's just go through the numbers one at a time. Maybe p divides a1. Well, if so, we're done, right? So maybe, stop spitting. You're gonna puke. Good. Maybe p divides a1. Well, if that's not that word. Maybe does not need to be there. If p divides a1, we're done. Does everyone see what I mean by we're done? Because all I need to show is that if p divides the product of these two numbers, then it has to divide one of them. Well, if it divides the first one, we're done. Okay, good. So suppose it doesn't. Suppose p doesn't divide a1. All right. Well, if p doesn't divide a1, it's also certainly true that a1. Oh wait, hold on. Do I need to even say that? If p doesn't divide a1, a1 certainly doesn't divide p because p is a prime. So that means that they have no factors in common. Wait, why is that true? Yes.
Can't you just say that A1 divides the product of A1 and A2, and if P doesn't divide A1, then it, like...
Why?
Yeah. Because it's like an integral, right?
Yeah, you guys, what's happening right now is the room is basically telling me proof by, yeah, just duh. I mean, I think that's what you're kind of saying, right? If P doesn't go into A1, it just has to go into A2. What are we even doing? It's a very low-level proof.
No,
I agree
no,
that, yeah.
No,
I think he's doing the transitivity of divisibility.
Yeah.
That if P divides A1 and A1 divides A1 and A2, then P1 divides A1 and A2. So I think, well, I guess you just have to do that twice.
For each.
Sorry, back up.
Are you proving the contrapositive, or are you
No,
just...
I am proving, I'm supposing that P divides A1 times A2, and then I'm going to show that it divides one of them. It has to divide one of these. Has to divide one of these two. If it doesn't divide A1, well, now I'm going to show that it. Then I'm going to show that it must divide A2. And this. I mean, I don't know. Do you have sort of thoughts about how you would want to do this, or what that even means? Yeah, Ethan.
Wait, do we want to do contradiction, but like
Yeah.
with, because if you also have if P divides A2, then we're also done, so the only case is if it doesn't divide either. Yeah.
Which is just.
I mean,
Yeah.
that's contradiction.
Right.
Oh yeah. If you want
Yeah,
to.
just do that.
Okay.
Just show that if it
So, but if it doesn't divide either, then what?
Then there's a
contradiction.
contradiction. And that's
Okay.
just done, because then like,
Okay, I agree with the logic, but do you know how to prove that?
Yeah. Yeah.
Oh, really?
You said like,
So you read it. I was like,
P
that's
doesn't-
remainder.
if you already know P divides A1, A2, and you can like.
Yeah. It's
Wait, can you just like write out the set of factors of
Like,
A1 and then say
It's
P
a
isn't in that and then write out the set of factors of A2 and then P isn't
Okay,
in that.
okay, so yeah, so perhaps I should mention that this is actually, this proof, upon completion, is going to be a lemma for proving the fundamental theorem of arithmetic, which we've talked about for 2 blocks now but haven't proven yet. Fundamental theorem of arithmetic, which Eob is asking if could we just use that? Well, yeah, of course, then it's just like trivial, right? Fundamental theorem of arithmetic says any number can be expressed as a product of primes. So I'm gonna use this to prove the fundamental theorem of arithmetic. Yeah, Ethan.
Wait, if you assume it's not in either, and you write A1 as the Euclidean division algorithm result,
Yeah.
and then,
Yeah. Did you just come up with that, or you just look in the book? Okay. Ethan did it out of nowhere. Yeah, that's exactly what they do. But I think I can just do it. I could just do it with this one, and then I think it ends up just working, right? So if P doesn't divide A1, then wait. You said you're talking about the thing we did last class, the Euclidean.
Yeah, worse than that.
You're talking about the Euclidean division algorithm.
yeah. What is it then? Oh, I don't
So
know.
the GCD of two numbers is that thing?
Right.
Yeah, yeah, you use that.
Yeah, that's how Gauss does it. He says, okay, if P, make sure I got this. If P doesn't divide A1, then the GCD of P and A1 must be 1. Why is that true?
There's no.
Oh yeah, because right, so the greatest common divisor of these two numbers, P and A1, has to be 1 because.
Oh yeah, because
Because P is prime. So if P doesn't divide A1, and the only factors of P are P and A1, and since P doesn't divide A1, then there's no other factor of P. So
Wait, can you repeat that?
yes, I said it pretty crappy, so I will repeat it. I claim that the greatest common divisor of P and A1